In physics, a wave is an oscillation accompanied by a transfer of energy that travels through space or mass. Frequency refers to the addition of time. Wave motion transfers energy from one point to another, which may or may not displace particles of the transmission medium. Disambiguation needed, that is, with little or no associated mass transport. Waves consist, instead, of oscillations or vibrations, around almost fixed locations. There are two main types of waves. Mechanical waves propagate through a medium, and the substance of this medium is deformed. The deformation reverses itself owing to restoring forces resulting from its deformation. For example, sound waves propagate via air molecules colliding with their neighbors. When air molecules collide, they also bounce away from each other. This keeps the molecules from continuing to travel in the direction of the wave. The second main type of wave, electromagnetic waves, do not require a medium. Instead, they consist of periodic oscillations of electrical and magnetic fields originally generated by charged particles, and can therefore travel through a vacuum. These types of waves vary in wavelength, and include radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. Waves are described by a wave equation which sets out how the disturbance proceeds over time. The mathematical form of this equation varies depending on the type of wave. Further, the behavior of particles in quantum mechanics are described by waves. In addition, gravitational waves also travel through space, which are a result of a vibration or movement in gravitational fields. A wave can be transverse or longitudinal. Transverse waves occur when a disturbance creates oscillations that are perpendicular to the propagation of energy transfer. Longitudinal waves occur when the oscillations are parallel to the direction of energy propagation. While mechanical waves can be both transverse and longitudinal, all electromagnetic waves are transverse in free space. General features. A single, all-encompassing definition for the term wave is not straightforward. A vibration can be defined as a back-and-forth motion around a reference value. However, a vibration is not necessarily a wave. An attempt to define the necessary and sufficient characteristics that qualify a phenomenon to be called a wave results in a fuzzy borderline. The term wave is often intuitively understood as referring to a transport of spatial disturbances that are generally not accompanied by a motion of the medium occupying this space as a whole. In a wave, the energy of a vibration is moving away from the source in the form of a disturbance within the surrounding medium. However, this motion is problematic for a standing wave, where energy is moving in both directions equally, or for electromagnetic waves in a vacuum, where the concept of medium does not apply and interaction with a target is the key to wave detection and practical applications. There are water waves on the ocean surface, gamma waves and light waves emitted by the sun, microwaves used in microwave ovens and in radar equipment, radio waves broadcast by radio stations, and sound waves generated by radio receivers, telephone handsets and living creatures, to mention only a few wave phenomena. It may appear that the description of waves is closely related to their physical origin for each specific instance of a wave process. For example, acoustics is distinguished from optics in that sound waves are related to a mechanical rather than an electromagnetic wave transfer caused by vibration. Concepts such as mass, momentum, inertia, or elasticity become therefore crucial in describing acoustic wave processes. This difference in origin introduces certain wave characteristics particular to the properties of the medium involved. For example, in the case of air, vortices, radiation pressure, shock waves etc. In the case of solids, Rayleigh waves, dispersion, and so on. Other properties, however, although usually described in terms of origin, may be generalized to all waves. For such reasons, wave theory represents a particular branch of physics that is concerned with the properties of wave processes independently of their physical origin. For example, based on the mechanical origin of acoustic waves, a moving disturbance in space-time can exist if and only if the medium involved is neither infinitely stiff nor infinitely pliable. If all the parts making up a medium were rigidly bound, then they would all vibrate as one, with no delay in the transmission of the vibration and therefore no wave motion. On the other hand, if all the parts were independent, then there would not be any transmission of the vibration and again, no wave motion. Although the above statements are meaningless in the case of waves that do not require a medium, they reveal a characteristic that is relevant to all waves regardless of origin. Within a wave, the phase of a vibration is different for adjacent points in space because the vibration reaches these points at different times. Mathematical description of one-dimensional waves. Wave equation. Consider a traveling transverse wave on a string. Consider the string to have a single spatial dimension. Consider this wave as traveling in the direction in space. E.g., let the positive direction be to the right, and the negative direction be to the left, with constant amplitude, with constant velocity, whereas independent of wavelength, independent of amplitude, with constant waveform, or shape. This wave can then be described by the two-dimensional functions or, more generally, by D'Alembert's formula, representing two-component waveforms and traveling through the medium in opposite directions. A generalized representation of this wave can be obtained as the partial differential equation. General solutions are based upon Duhamel's principle. Waveforms. The form or shape of f in D'Alembert's formula involves the argument x minus Vermont. Constant values of this argument correspond to constant values of f, and these constant values occur if x increases at the same rate that Vermont increases. That is, the wave shaped like the function f will move in the positive x direction at velocity v. In the case of a periodic function f with period lambda, that is, f equals f, the periodicity of f in space means that a snapshot of the wave at a given time t finds the wave varying periodically in space with period lambda. In a similar fashion, this periodicity of f implies a periodicity in time as well. F equals f provided vt equals lambda, so an observation of the wave at a fixed location x finds the wave undulating periodically in time with period t equals lambda v. Amplitude and modulation. The amplitude of a wave may be constant, or may be modulated so as to vary with time in, or position. The outline of the variation in amplitude is called the envelope of the wave. Mathematically, the modulated wave can be written in the form, whereas the amplitude envelope of the wave is the wave number and is the phase. If the group velocity is wavelength independent, this equation can be simplified as showing that the envelope moves with the group velocity and retains its shape. Otherwise, in cases where the group velocity varies with wavelength, the pulse shape changes in a manner often described using an envelope equation. Phase velocity and group velocity. There are two velocities that are associated with waves, the phase velocity and the group velocity. To understand them, one must consider several types of waveform. For simplification, examination is restricted to one dimension. The most basic wave may be expressed in the form, which can be related to the usual sine and cosine forms using Euler's formula. Rewriting the argument makes clear that this expression describes a vibration of wavelength traveling in the x direction with a constant phase velocity. The other type of wave to be considered is one with localized structure described by an envelope, which may be expressed mathematically as, for example, where now A is a function exhibiting a sharp peak in a region of wave vectors delta k surrounding the point k1 equals k, in exponential form, without the magnitude of A. For example, a common choice for AU is a Gaussian wave packet, where sigma determines the spread of k1 values about k, and n is the amplitude of the wave. The exponential function inside the integral for psi oscillates rapidly with its argument, say phi, and where it varies rapidly. The exponentials cancel each other out, interfere destructively, contributing little to psi. However, an exception occurs at the location where the argument phi of the exponential varies slowly. The condition for phi to vary slowly is that its rate of change with k1 be small. This rate of variation is where the evaluation is made at k1 equals k because A is centered there. This result shows that the position x where the phase changes slowly, the position where psi is appreciable, moves with time at a speed called the group velocity. The group velocity therefore depends upon the dispersion relation connecting omega and k. For example, in quantum mechanics the energy of a particle represented as a wave packet is E equals h omega equals 2. Consequently, for that wave situation, the group velocity is showing that the velocity of a localized particle in quantum mechanics is its group velocity. Because the group velocity varies with k, the shape of the wave packet broadens with time, and the particle becomes less localized. In other words, the velocity of the constituent waves of the wave packet travel at a rate that varies with their wavelength. So some move faster than others, and they cannot maintain the same interference pattern as the wave propagates. Sinusoidal waves. Mathematically, the most basic wave is the one-dimensional sine wave with an amplitude described by the equation. Where is the maximum amplitude of the wave? Maximum distance from the highest point of the disturbance in the medium to the equilibrium point during one wave cycle. In the illustration to the right, this is the maximum vertical distance between the baseline and the wave. Is the space coordinate? Is the time coordinate? Is the wave number? Is the angular frequency? Is the phase constant? The units of the amplitude depend on the type of wave. Transverse mechanical waves have an amplitude expressed as a distance. Longitudinal mechanical waves use units of pressure, and electromagnetic waves express the amplitude in terms of its electric field. The wavelength is the distance between two sequential crests or troughs, generally as measured in meters. A wave number, the spatial frequency of the wave in radians per unit distance, can be associated with the wavelength by the relation the period is the time for one complete cycle of an oscillation of a wave. The frequency is the number of periods per unit time and is typically measured in hertz. These are related by. In other words, the frequency and period of a wave are reciprocals. The angular frequency represents the frequency in radians per second. It is related to the frequency or period by the wavelength of a sinusoidal waveform traveling at constant speed is given by, where is called the phase speed of the wave and is the wave's frequency. Wavelength can be a useful concept even if the wave is not periodic in space. For example, in an ocean wave approaching shore, the incoming wave undulates with a varying local wavelength that depends in part on the depth of the sea floor compared to the wave height. The analysis of the wave can be based upon comparison of the local wavelength with the local water depth. Although arbitrary wave shapes will propagate unchanged in lossless linear time invariant systems, in the presence of dispersion the sine wave is the unique shape that will propagate unchanged but for phase and amplitude, making it easy to analyze. Due to the Kramers-Kronig relations, a linear medium with dispersion also exhibits loss. So the sine wave propagating in a dispersive medium is attenuated in certain frequency ranges that depend upon the medium. The sine function is periodic, so the sine wave or sinusoid has a wavelength in space and a period in time. The sinusoid is defined for all times and distances, whereas in physical situations we usually deal with waves that exist for a limited span in space and duration in time. Fortunately, an arbitrary wave shape can be decomposed into an infinite set of sinusoidal waves by the use of Fourier analysis. As a result, the simple case of a single sinusoidal wave can be applied to more general cases. In particular, many media are linear, or nearly so. So the calculation of arbitrary wave behavior can be found by adding up responses to individual sinusoidal waves using the superposition principle to find the solution for a general waveform. When a medium is nonlinear, the response to complex waves cannot be determined from a sine wave decomposition. Plane waves. Standing waves. A standing wave, also known as a stationary wave, is a wave that remains in a constant position. This phenomenon can occur because the medium is moving in the opposite direction to the wave, or it can arise in a stationary medium as a result of interference between two waves traveling in opposite directions. The sum of two counterpropagating waves creates a standing wave. Standing waves commonly arise when a boundary blocks further propagation of the wave, thus causing wave reflection, and therefore introducing a counterpropagating wave. For example, when a violin string is displaced, transverse waves propagate out to where the string is held in place at the bridge and the nut, where the waves are reflected back. At the bridge and nut, the two opposed waves are in antiphase and cancel each other, producing a node. Halfway between two nodes there is an antinode, where the two counterpropagating waves enhance each other maximally. There is no net propagation of energy over time. One-dimensional standing waves, the fundamental mode and the first 5 overtones. A two-dimensional standing wave on a disk, this is the fundamental mode. A standing wave on a disk with two nodal lines crossing at the center, this is an overtone. Physical properties. Waves exhibit common behaviors under a number of standard situations. Transmission and media waves normally move in a straight line through a transmission medium. Such media can be classified into one or more of the following categories. A bounded medium if it is finite in extent, otherwise an unbounded medium. A linear medium if the amplitudes of different waves at any particular point in the medium can be added. A uniform medium or homogeneous medium if its physical properties are unchanged at different locations in space. An anisotropic medium if one or more of its physical properties differ in one or more directions. An isotropic medium if its physical properties are the same in all directions. Absorption of waves mean, if a kind of wave strikes a matter, it will be absorbed by the matter. When a wave with that same natural frequency impinges upon an atom, then the electrons of that atom will be set into vibrational motion. If a wave of a given frequency strikes a material with electrons having the same vibrational frequencies, then those electrons will absorb the energy of the wave and transform it into vibrational motion. Reflection. When a wave strikes a reflective surface, it changes direction, such that the angle made by the incident wave and line normal to the surface equals the angle made by the reflected wave and the same normal line. Interference waves that encounter each other combine through superposition to create a new wave called an interference pattern. Important interference patterns occur for waves that are in phase. Refraction is the phenomenon of a wave changing its speed. Mathematically, this means that the size of the phase velocity changes. Typically, refraction occurs when a wave passes from one medium into another. The amount by which UV is refracted by a material is given by the refractive index of the material. The directions of incidence and refraction are related to the refractive indices of the two materials by Snell's law. Diffraction. A wave exhibits diffraction when it encounters an obstacle that bends the wave or when it spreads after emerging from an opening. Diffraction effects are more pronounced when the size of the obstacle or opening is comparable to the wavelength of the wave. Polarization. A wave is polarized if it oscillates in one direction or plane. A wave can be polarized by the use of a polarizing filter. The polarization of a transverse wave describes the direction of oscillation in the plane perpendicular to the direction of travel. Longitudinal waves such as sound waves do not exhibit polarization. For these waves, the direction of oscillation is along the direction of travel. Dispersion: a wave undergoes dispersion when either the phase velocity or the group velocity depends on the wave frequency. Isaac Newton performed experiments with light and prisms, presenting his findings in the optics that white light consists of several colors and that these colors cannot be decomposed any further. Mechanical waves. Waves on strings. The speed of a transverse wave traveling along a vibrating string is directly proportional to the square root of the tension of the string over the linear mass density, where the linear density mu is the mass per unit length of the string. Acoustic waves. Acoustic or sound waves travel at speed given by or the square root of the adiabatic bulk modulus divided by the ambient fluid density. Water waves. Ripples on the surface of a pond are actually a combination of transverse and longitudinal waves, therefore, the points on the surface follow orbital paths. Sound, a mechanical wave that propagates through gases, liquids, solids and plasmas. Inertial waves, which occur in rotating fluids and are restored by the Coriolis effect. Ocean surface waves, which are perturbations that propagate through water. Seismic waves. Shock waves. Other waves of traffic, that is, propagation of different densities of motor vehicles, and so forth, which can be modeled as kinematic waves. Metachronal wave refers to the appearance of a traveling wave produced by coordinated sequential actions. It is worth noting that the mass-energy equivalence equation can be solved for this form.